the directional derivative of a function f, let's say z equal f of xy, in the direction of certain vector u at the particular point AB, measures the rate of change of this surface in this direction. So if we get, for instance, that this derivative equals to 3, so that will mean that in this particular direction, this surface is increasing with a rate of change equal to 3. So the way to calculate, the way to define this directional derivative is the familiar formula for the derivative, only that now we are going to increase in the direction of the vector u, which is u1, u2, and this increase here is going to go to 0. In order to calculate this derivative, this theorem will give us a practical way to calculate, since it says that the directional derivative is also equal to this formula, which says that the directional derivative at a point xy is going to be equal to the partial derivative respect to x of the function at the point xy multiplied by the first component of the vector, and then the partial derivative respect to y at the point xy multiplied by the second component of the unit vector, u1, u2. So this theorem gives us a very practical way to calculate a directional derivative. Essentially, all what we need is a unit vector in the direction that we want the derivative, and we know how to make any vector to be unit, right? So we know how to normalize a vector, and we need also the partial derivatives of the function. So, for instance, let's consider this surface. This surface will have some drawing here. This will be a surface like this. Let's calculate in general what could be the directional derivative of the function in a generic point xy. So in order to do that, we know that we are going to need the partial derivatives. Let's start. The partial derivative respect to x at xy is going to be, the derivative respect to x of this function is going to be 2x minus y. And then the derivative respect to y of this function is going to be minus x minus 2. And so we need to normalize the vector. Let's say that in this case we want to do the derivative in the direction of the vector 2, 1. And so the first thing that we need to do with this vector is to find its norm so we can normalize it. So the norm will be the square root of each of the components here. So that will be 2 squared, which is 4, plus 1. So the norm is a square root of 5. And so we know that the vector normalized is going to be equal to the vector 2 over square root of 5, 1 over square root of 5. And so this is all the data that we need, these three things, in order to calculate the directional derivative according with the theorem that we just saw. And so the directional derivative in the direction of the vector u of the function f at the point xy is going to be equal to the partial derivative respect to x, which is 2x minus y, times the first component of the vector, which is 2 divided the square root of 5, plus the derivative respect to y, which is minus x minus 2, times the second component of the vector, which is 1 over square root of 5. Okay, and now we do the operations here. Let's take 1 over the root of 5 as a common factor, and we have here everything multiplied by 2. That will be 4x minus 2y, and so here will be plus minus will be minus x minus 2. And then we combine like terms, and this is 1 over square root of 5 times 4x minus x is 3x minus 2y minus 2. So we have here then the directional derivative then of this function in this direction at any generic point xy. If we want it at a particular point, we can plug in the particular point that we want the the directional derivative. We can see that what we needed in the directional derivative are the partial derivatives of respect to x and respect to y. So we're going to define now a vector that is just a vector that the components are going to be exactly those, the partial derivative respect to x and the partial derivative respect to y. This is one of the most important vectors in multivariable calculus. It's called the gradient of the function, and the gradient is a vector whose components are just the partial derivatives. This is in general for any x, y, so we can say that the gradient at xy is just the derivative of f respect to x at xy and the derivative of f respect to y at xy. So this vector is the gradient of the function. And so looking back at this theorem what we were calculating here, so here we have the components of the gradient. And if we observe the formula that we have here, we could see that this is the component of the gradient times u1 and the component of the gradient times u2. So you can recognize here the formula of the dot product, right? We are multiplying two first components of two vectors and the second components of these two vectors. So putting together all this, we can say then that the directional derivative is nothing but the dot product of the gradient dot product the unit vector. So then we have like a very practical way to calculate the directional derivative. It's just the dot product of the gradient dot product with the unit vector in which direction we want to calculate the directional derivative. For example, in our previous example where we calculate the directional derivative of this function in the direction of this vector, we can now calculate directly this by saying, well, the gradient of the function is the vector 2x minus y minus x minus 2, right? The two partial derivatives that we have calculated before. And the unit vector is just 2 divided the square root of 5, comma, 1 divided the square root of 5. So then the directional derivative of the function and xy is going to be the dot product of these two vectors, which means 2x minus y times this plus minus x minus 2 times the other. So this is exactly the formula that we have seen before. Now, knowing that this is the dot product, we have also a way to remember how to do the directional derivative. So knowing also that is the dot product, so we can put here in place everything that we know about the dot product. So we know that, let's remind you that the directional derivative of a function at a point is the dot product of the gradient times the unit vector u. Well, we know that the dot product, the definition of dot product is given as the norms of the two values, the multiplication of the norms of the two vectors times the cosine of the angle that they form. So we know that this is the same thing that the norm of the gradient times the norm of u times the cosine of the angle that they form. I mean, if this is the gradient and this is the vector u, so this is the angle that they form. But we know that u is a unit vector, so this is just 1. So what we have is that the directional derivative is just the norm of the gradient times the cosine of the angle that they form. And so this is just a multiplication of numbers, right? These two things are numbers. So and we know that the cosine is a number that goes between -1 and 1. So we know that this number here is going to be equal to the norm of the gradient multiplied by a number that is between -1 and 1. So we know then that we are going to get a maximal value when the cosine is 1 and a minimal value when the cosine is -1. And so we know also what angle is when the cosine is 1, right? If we have a trigonometric circle, this is an angle. We know that this is the sine and this is the cosine. So we know that the cosine equals 1 exactly when the angle is 0, right? Or 180. So I mean 180 will be -1, right? So it's 1 when it's 0 and -1 when it's 180. So we can study when this derivative is going to be maximal. I mean, when the rate of change of the function is going to be the maximal possible. When it's going to be the maximal possible when this cosine is 1, which means when the angle between these two is 0. In other words, when the direction u is the same direction that the gradient. So we deduce then that the direction in which the derivative indicates the maximal rate of change is actually the direction of the gradient. And by the other hand, when it's the minimal, it's going to be the opposite direction of the gradient. Okay, so observing all these things, we can state these properties of the gradient. So, for instance, if the gradient happens to be 0, well, we are doing the dot product here with a multiplication by 0. The directional derivative is going to be 0, no matter what is this, right? So that means that no matter in what direction, if the gradient is 0, the directional derivative is going to be equal to 0 for all directions u. Also, the second property tells us that if the gradient is not 0, it's not the vector 0, so then the directional derivative is going to be maximal for what direction? For the direction of the gradient, as we said before, right, when the cosine is equal to 1. And moreover, this maximum value, so when this is equal to 1, the directional derivative will be just equal to the norm of the gradient. So the second property tells us two things. First, that the direction in which the rate of change is maximal is the direction of the gradient. And then tell us also what is that rate of change. How much is the directional derivative? Well, it's going to be just the norm of the gradient. And the same thing about the minimal. It's going to be minimal when the direction is the direction opposite to the gradient, and the minimal value is going to be equal to minus the gradient, because then the cosine here is going to be -1. So for instance, let's apply this to calculate. Let's see this example. Find the direction for which the directional derivative of this function at -1, 3 is maximal, and find actually the maximal value. Well, we know that the direction in which the derivative is going to be maximal, we know that is the direction of the gradient, right? So what we are asked to calculate then is what is the gradient, because that is the direction in which it's going to be maximal. And then what is the maximal value? Well, it's going to be the norm of that gradient. So essentially all what we need is to calculate the gradient. So let's do that. So let's start by calculating. This was the same function that we had before. So we can calculate the derivatives. We already have them. So we have already that the gradient of this function at a point xy was 2x minus y minus x minus 2. So now we need to evaluate this gradient at the point minus 1, 3. So we evaluate that. So that will be 2 times minus 1 minus 3. And then it's going to be 1 positive minus 2. So the gradient is going to be just the vector minus 5 minus 1. So we calculate the gradient. So this is the answer to the first question, right? What's the direction? Well, it's the direction of this vector. In this direction is where the function is going to increase the maximum. And how much is this maximal value? In other words, we need to calculate what is the directional derivative in the direction of u. But now u is the gradient of f minus 1, 3, right? So it's this particular direction u. So, and this is going to be the norm of the gradient, which is just the root of this, which is the root of 26. Okay, so this is then the maximal value of the derivative. Of course, this derivative we could also calculate it directly, right? So we could calculate this derivative. So this is the way to calculate according to the properties. But we could calculate this derivative directly. So the derivative in the direction of this vector, that is minus 5 minus 1, will be at the point minus 1, 3, will be, according to the original formula, the gradient of f at minus 1, 3 dot product this vector normalized, the vector minus 5 minus 1 normalized. And so we do the dot product of these two. This vector is a vector that we calculated before, minus 5 minus 1, times this vector normalized, minus 5 square root of 26 minus 1 square root of 26. And we do the operation here. We have minus is plus, 25 plus 1 is 1, divided the square root of 26, 26 divided the square root of 26. That if we multiply numerator and denominator by the square root of 26, we have a square root of 26 squared, that is just 26. Canceling, this is a square root of 26. Of course, it's the same result that we obtain directly by the property. So we have also that this very important vector, the gradient of the function, if it's not 0, this vector is always going to be perpendicular to the level curve. So let's suppose that this is the surface here, and we have at certain point here, we have a level curve here. That is the level curve. So the vector that is perpendicular, the direction that is perpendicular to this level curve, this is going to be the direction of the gradient. I mean, the direction in which this function is growing the fastest. And extended to three dimensions, we have that if the function has 3 variables, so what's going to happen is that the gradient is going to be also perpendicular, normal, to the level surface of the function at the point.